Hi, rock stars. We're going to talk a lot about legal perspectives and others throughout the course. But as we get started, I invited my friend Ben, who's an engineer at Nokia, to come talk about this from more of a tech perspective and get us started for that. And with that, I want to turn it over to Ben and have him introduce himself.
Okay, so I'm going to just dive in and share my screen. Okay, hi everybody. So I'm going to today give an overview of artificial intelligence and machine learning, and just a little bit of background about myself. So I've been in the wireless industry for 28 years. I've worked on 2G, 3G, 4G LTE, and 5G, and I'm starting to work on 6G. I'm a standards engineer, and I've been a system architect. And I'm currently working on Open Radio Access Network, ORAN standards. I have a number of patents. And before I was working at General Electric Medical Systems on ultrasound and MRI machines. And I've worked as some other things I've done, like Habitat for Humanity. I've been in a volunteer at an emergency room. I was a librarian, a recruiter, a photographer. I'm currently the Bell Labs photographer. I've been a teacher, guide, and judge. I have a master's and bachelor's in electrical engineering, Purdue University, and a PhD in operations research from Walden. One of my hobbies is traveling. I've been to 31 countries and 6 continents, and I'm trilingual. And I've authored 6 books, the latest of which are The 4 Elements of Thinking in 2019 and The Periodic Table of Ideas in 2021. I've published 18 games, and I'm a former HeroClix world champion. So I'm going to cover these sort of 5 areas: AI/ML overview and key concepts. What are some of the biggest ideas in AI and ML? Give you an overview and some of the overarching principles. And then we'll dive into a deeper dive into some of the key machine learning ideas, and then a little bit of a history of AI/ML and a little bit of its possible future and prognostication. And then some AI/ML applications and some of the players in some applications. Okay, so the first step is what are an overview. So AI/ML is artificial intelligence, machine learning, and deep learning. AI/ML/DL are things you'll hear a lot, and they're things that we're going to dive into in more detail. So artificial intelligence are programs and machines that learn, reason, and make intelligent decisions. Machine learning are machines that learn through experience without explicit programming. And deep learning are a specific kind of form of machine learning that utilizes artificial neural networks that can adapt, learn, and make intelligent decisions. So let's look at that first box for a second. So artificial intelligence kind of has 3 flavors. It's or 3 progressive steps or stages. So the first is called artificial narrow intelligence, and it's basically what some people call weak AI, and it has narrow capability. Think like the 1980s and 1990s expert systems. They're algorithmic, and they're good for data mining and pattern recognition and human-computer partnerships and like navigation systems. Now we're largely right now in this era of artificial narrow intelligence, and you see how it's already super useful. Now it may sound that weak AI may sound not so flattering, but it's actually tremendously amazing the things that we can do with artificial narrow intelligence, which is essentially where we are now. The next is artificial general intelligence, or AGI, and strong AI. And it has the ability to recognize, to learn, machine vision, and process language. So we're kind of in that, you see, dipping our toes into the area of AGI, and some of the foundations of that are being built. The last stage is what's called artificial superintelligence, or strong AI. And it has a transcendent ability, the ability to be creative, to innovate, to plan, decide, forecast, and with advanced robotics and communications. So ANI, or weak AI, or artificial narrow intelligence, is always has some kind of problem to solve or some kind of task to do. So it revolves around something that is trying to accomplish a particular task. And I was told that you had read the book You Look Like a Thing and I Love You. And in that book, you'll recall how it talks about the AI performs better. Now, granted, that book was written 6 years ago and authored, 10 years ago, but but ANI works well, and that's true still today. When you have a narrow problem to define, the narrower the problem, the more focused the problem, the better AI performs, which is still true for ANI type things, right? So if you have a very focused task, set your house lights to 50%, it can do that very well because, if you narrow that task, ANI does well because you narrow the problem space that it has to work with. Artificial general intelligence, by contrast, is a very open-ended sort of thing. It doesn't have a specific necessary problem to solve, but it has like sort of an environment to navigate. So think like WALL-E from the Disney WALL-E movie, or C-3PO from Star Wars. It still might have a specific kind of task to do, like C-3PO is a language translator or WALL-E is a garbage collection thing. But it's a much more versatile thing, right? It's actually solving hundreds, if not thousands, of problems. Think of WALL-E navigating through an environment or picking out specific things that are garbage or recognizing this is, something that's a living. And then artificial superintelligence has consciousness. It has maybe sentience and maybe a conscience. So like think Megan from the movie Megan, or Data from Star Trek, or David from the movie Artificial Intelligence. Okay, so let me take a kind of overview of how does AI/ML work at a 10,000-foot level, right? So at the top here, we see that and this is basically for ANI and AGI, right? So where we are now in 2025 largely is ANI and a bit into AGI. So, and we basically, all our modern algorithms in 2025 work with data and training. So there's some kind of data that it works with, and there's some kind of training, and that feeds into some kind of smart algorithm that then that algorithm sees how it does, it evaluates it, and deploys what it needs to make decisions and to take the next steps. So let's first take a look at data and training. So again, the modern AI now, as of right now, generally has some kind of task or problem to solve, or a set of problems and a set of tasks to solve. And so that's the first thing that's very important, to define that task very carefully, and to be able to express what the goals of what you're trying to get the AI to do. Next, there's data collection. So either there's a huge set of data already available, or you have to somehow generate your data. But there has to be, generally speaking, some sort of data for at least for ANI, our modern AI algorithms to work. And there might be some data pre-processing, some cleaning or formatting of the data before you put it into the training algorithm. And you recall from the book, like, there can be biases in data, right? So especially if you're trying to train like an AML thing on socially related sort of stuff, and then there's training that happens. So you put in the data into the algorithm, and it might start with just some sort of random numbers, but eventually it learns to adjust those parameters to minimize model errors. Next are some of the key features of the smart algorithm. So through the data, it eventually can find patterns or features, what are called features or characteristics from that raw data. The algorithm, the AML algorithm itself, and we'll talk a lot more about that through the rest of this lecture. And then, as a result of training, or what are called epochs, each pass through the algorithm, you'll tweak the weights, or it'll learn, right? The algorithm gets better. And we'll also talk about supervised, semi-supervised, and unsupervised, and reinforcement learning. So there are lots of different models to how the data might start labeled or unlabeled, or a mixture of those two things, or the kind of problem that it's looking at. And finally, once you have the algorithm, it's generally trying to make some sort of prediction or some sort of decision, and that trained algorithm has some sort of output, right? For example, maybe you're sorting pictures of having to try to have it recognize images of something, or maybe you're trying to have it control some system. And uh, and then there's some sort of evaluation metric to see how it's doing against what its goals are, right? Against the problem that it's trying to solve. So now, it has to be noted that this slide is really high level, right? It's a 10,000-foot view of AIML, and there are lots and lots of variations of AIML, and not everything follows perfectly into these things. This is just a good sort of roadmap for you, a mental roadmap for you to have in your mind to see this is roughly how AIML works. Like it takes some sort of data for the most part. It's having to solve some sort of problem. There's some sort of data it's collecting and processing. You're training, you're usually training an algorithm. And that algorithm is detecting some features and it spits out some sort of prediction and decision. And then there's usually some sort of feedback mechanism to improve the algorithm as it goes. So, okay, so now we're going to take a look at some of those machine learning methods, and we'll dive a little bit deeper into the machine learning aspects. So one really important concept in machine learning is the different kinds of learning there are. So we'll start with unsupervised learning. So in unsupervised learning, the algorithm itself is just simply, there's no guidance at all. It's just simply on its own, trying to find patterns and groupings and to identify clusters of information without any sort of direction, right? So they're clustering unlabeled data sets, and it might be working towards visualizing big data. Next is supervised learning. So in supervised learning, you sort of think about it like an archer shooting a target, right? So there's some sort of very directed goal. Whereas unsupervised learning might be playing with Lego blocks, right? There's nobody telling you what to build. You just go ahead and build something. Whereas supervised learning, I generally have some very specific task or goal or objective that I'm trying to aim at. And so I might label what's called labeling data. So I'll classify data to help the algorithm achieve those particular targets and for it to gauge against proper and correct answers. And next, you can have a combination of those where it's called semi-supervised learning, where you mix together combinations of labeled and unlabeled data. And you might start with some categories and examples. And a good example of this is like if the first thing is sort of like playing with Legos and the second is sort of a very goal-directed target, the third category is kind of like a teacher in a classroom, right? Like what you're going through right now, where a teacher will give you some guidance, but you'll go off and study and learn on your own as well, right? So there'll be some guided activities and some unguided activities for you to try to master the concepts. And finally, reinforcement learning is probably the hardest to get your mind around, and it's the most complex of the ML algorithms, but it's also one of the most powerful. So it uses very simply, very easy to picture like a carrot and a stick, right? So there's reinforcement learning allows the algorithm to perform some kind of activity or task and then gauge how well it's doing. So I have a couple cartoons here to try to illustrate this. So we see here on the left a supervised learning where labeled data sets. So here a person is basically saying these are apples, right? And I'm trying to have you identify, I want the algorithm to identify to be able to pick out apples, right? And in their various orientations and various shades. And one thing that we've learned over the decades is that machine vision is actually kind of a complex and hard thing to solve. We thought, oh, it'd be easy because we take it so much for granted. But consider some of the things that you have to consider for machine learning for vision, right? If something is partially behind another object, imagine like, 70% of the apple is covered by an orange. Is that still an apple? Is that an apple behind the orange? Or consider like something that is causing a shadow over the apple, right? Is that black blotch, is that still an apple? We naturally just very easily figure that out. And so we were a long time ago, decades ago, we thought that this would be trivial and easy, but it turns out machine vision is a very interesting, difficult problem to solve. So for unsupervised learning, we see here on the cartoon on the right, um, there's nothing guiding the algorithm. It's making um, decisions on its own and groupings on its own. So in the cartoon here, it's observing that those three things are like each other. Those three apples are alike, and those three bananas are alike.
My favorite example from that is when they used unsupervised learning to train an AI on tumor spotting. And
Yeah.
the AI thought that having a ruler in the picture meant there
Oh,
was a
yeah.
tumor,
Yes.
because
That's
most of
right.
the examples
Yes.
they had were
Yes.
had a tumor had a ruler to measure how big the tumor was.
Right. 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 Yeah. That was interesting. An example from that book. Okay. So semi-supervised learning, the diagram here I'm using it's showing how basically there's some labeled data. So and it must be noted that labeling data can be very time consuming and very laborious, right? So it can be difficult to label a bunch of data, right? And so in this case, we're labeling some of the data. We're showing you this is a banana, these are oranges, and there's maybe usually a much, much larger data set of unlabeled data. So maybe I'm labeling 100 pictures, and here's pictures of bananas and oranges, but here's 10,000 pictures of just fruit that's not labeled. And so when the machine learning, semi-supervised machine learning algorithm comes along and comes across a new picture, let's say of an apple, it's then crunches it through its algorithm and it's able to predict that's an apple. Another good example of this is like if I have an algorithm that I want to detect celebrities, right, or a particular celebrity. So if you want an algorithm that can detect Taylor Swift, maybe you show a few images of Taylor Swift in various, performances, and then show 10,000 pictures of where she's also at, but you don't label it, right? So and you have, or maybe she's with other celebrities, and you have the algorithm try to learn that way. So that's an example of semi-supervised learning. Reinforcement learning, a good example of that is think of something trying to traverse a maze. Reinforcement learning is also used to like play video games where there's some sort of environment the that the thing is playing in, and it can take specific actions: left, right, jump, duck, walk, etc. And and then there's some sort of interpreter that's seeing how it's doing. Are you doing well? Did you get closer to where you're trying to get to? And through that reward and that current, it might have certain current states to represent what's going on in the screen or the maze. And it can take actions based on rewards. Okay, so now we're going to dive into some of the algorithms and some of the more specific kinds of methods that are used for these various things. And we'll see how they work in a little bit more detail. So for unsupervised learning, there's a method called Apriori Association where we calculate the support and confidence, and we can group items to improve our lift. In k-means clustering, you're basically taking a bunch of data and kind of grouping them, just like I showed you in those cartoons. You're kind of grouping them into clusters. And then artificial neural networks, you've probably heard of that. Those are very popularly and very widely used. So there are neural networks that are used for unsupervised learning. Supervised learning, some examples of that are linear regressions, where we find and where we're looking for and finding a linear relationship between dependent data. Support vector machines is kind of like k-means clustering, where you're basically also grouping or categorizing things, and you're trying to find what's called a hyperplane, a dividing plane between the two groups. And a decision tree is kind of like it sounds. 20 questions is probably the best example of that, where we go through a branches of decisions to arrive at a leaf. And then semi-supervised learning, generative adversarial networks, or GANs, is an example of semi-supervised learning, and self-trained naive Bayes classifiers, where it trains on data through probabilistic statistics via the Bayes theorem. And then finally, reinforcement learning. There's model-based value estimation, which uses policy and value iterations, and Q-learning, which optimizes a state and action-based quality. So let's dive into each one of these. Apriori Association, again, it's an unsupervised machine learning method. And a good example of this is a video recommendation system, right? So think like Amazon, who recommends a book or movie based on what you've seen already. So what's the likelihood that a user who's already seen a particular movie, like Marjorie Prime, might like the movie WALL-E? So Marjorie Prime is a really great AI ML movie. I would suggest, I would recommend it. Really interesting and thought-provoking. And it's kind of related to WALL-E, right? They're both kind of artificial intelligence movies. And so the video recommendation engine then looks at a total number of users who saw, in the overall, let's say there were 100 total users in the system, and the users that saw WALL-E are with the blue smiley faces, and those who saw WALL-E and Marjorie Prime are the green faces. And so you can basically calculate a support, which is the number of elements that's seen both the green faces divided by the total number of elements, 100, right? So the support is 10 over 100, or 10%. And the confidence is the number of elements that have both elements against the elements that have with the WALL-E, right? So that the confidence calculation in this case would be 9, which is the number of green faces, over 40, which is the total number of combined X elements. And then the lift is the confidence divided by the support. So essentially, this algorithm, this kind of algorithm, it can be used for given some prior knowledge. What can I say about a predictive thing that you might like something? So these sort of recommendation things are a really good example, I think, of a use of a priori association. And you'll see different algorithms have sort of different fortes and different things too. We'll go over that in the summary slide. So k-means clustering, this is quite like that cartoon that we saw, right? Like you're presenting it with lots of different pictures of fruit, and it's clustering them into, these are kind of like each other. They're all these bananas, look kind of like the red area, shaded areas, and these all look like apples, the green shaded areas, and those all look like, oranges or kiwis in the blue shaded area. So in the first part, it starts with some sort of it starts with some sort of initial means, and perhaps that's randomly generated, and then I create clusters where I associate every data with some sort of observation near a mean, and I can calculate a centroid, and then after that I converge until I get these areas, such that when new pieces of data come in, if it's like a banana, I calculate it and it's going to come into this area, or if it's like an apple or kiwi, I'm able to classify and categorize new observations into each of these clusters. Okay, now artificial neural networks is a huge area of AIML, and there's lots and lots and lots of work on this. Artificial neural networks has been was first proposed in 1943, so it has 60 plus years behind it, and a lot of theoretical work behind it. But basically, what an artificial neural network is we thought, well, what if we create sort of digital neurons, right? Like we know uh, that brains are smart, right? Brains are conscious and they're sentient and they can make decisions and do all sorts of amazing things. And we know just through hundreds of years of science that the brain is composed of neurons. So what if we digitally emulate neurons? And maybe that's one way to achieve, artificial intelligence, right? And so lots and lots of study and algorithms and stuff have been proposed and developed utilizing that sort of concept. So the first we'll talk about is autoencoders, which learns to code unlabeled data and copy it from an input to output. And then encoding transforms that input data, and a decoding function recreates the input data from the encoded representation. So there's in any neural network, there's basically those initial neurons that you encounter, and maybe a neuron has like a weight, and it has basically sort of a transmission, right? So the if you think about what a human brain neuron does is there's some sort of the weight is how strongly it fires, right? And the brain is essentially an electrical based system. So and that weight or how strongly it fires is sort of emulated by the digital neural network. And then there's an output layer that tries to take those that input and spits an answer out, basically. A recurrent neural network is characterized by a direction of the flow of information between its layers, in contrast to the unidirectional feed-forward neural network. A bidirectional artificial neural network allows the output from some nodes to affect subsequent inputs to the same nodes. So it's sort of using like feedback and allowing different layers, one layer to affect another layer. Feed-forward neural networks are characterized by the direction of flow of information between its layers, and data moves in only one direction from input to hidden layers to output layers in a feed-forward neural network. So we'll see more examples about this when I talk about large language models a few slides from now, and this will be a little bit more apparent as we'll see an actual sort of live example of neural networks in action. Convolutional neural networks learn some sort of feature engineering. These are really good for like image processing. Vanishing gradients and exploding gradients are seen during backpropagation. Backpropagation is basically where I feed back the output and I adjust the weights. I take those and I propagate them backwards across the layers of the network and adjust the weights. And then earlier neural networks are prevented by using regularized weights over fewer connections. So in a convolutional neural network, remember I talked about features. So one layer of a convolutional neural network might be looking for like features like edges or eyes or a smile or a nose. And one layer's job might be purely just for edge detection, right? And then it feeds that into the next layer to find other like shapes. Oh, this one layer might be specially looking for eyeballs or a smile. Okay, so linear regression is a kind of supervised learning, and this is maybe one of the easier ones to wrap your head around. So basically, it's looking for basically a way that I can create a regression line along the training data. So I have, again, this sort of basic flow, where I have some data I'm training, I have some sort of smart algorithm, and that algorithm is generating some sort of output, and from that, and it's taking in some sort of input, and I'm looking at, given what I tried to predict, how did I do, right? And it can basically, this algorithm computes a relationship between the dependent target variable against the independent variable. So maybe I'm looking at, I'm trying to predict what the price of something should be, or how I should price something yeah, for some product that I have on the shelf if I'm a retailer. A support vector machine is really good at classifying stuff. So the idea here is that there are features that are, maybe I'm trying to separate, I'm trying to look at images, I'm trying to differentiate between images of cats and dogs. And I define some features of cats and some features of dogs. So maybe the amount of whiskers something has, or the amount of the size and shape of eyes that I can encode, or ears encode into a number. I combine those numbers and give it some sort of representation, or set of a vector, or set of numbers. And from those, I get data points, right? Each of these red points are data points. And again, this is supervised learning, so I tell it these are all, somebody's told it these are all cat pictures and these are all dog pictures. And then what I do is I calculate basically I calculate a dividing line between those two things, right? So I'm able to say something falling on this side of the dividing line is a cat. Something falling on that side of the dividing line is a dog. And there's some things that are very dog-like that are not cat-like at all. There's some things that are very cat-like and that are not dog-like at all. But maybe there's some cats and dogs that, maybe there's some dog-like kind of cats, and maybe there's some cat-like kind of dogs, right? They're harder to tell apart even in real life, right? And that dividing line is called a separating hyperplane. So support vector machines is a kind of supervised learning for classification and regression. Is really good for classification, right? Training examples belong to one of two categories, and a support vector training machine algorithm can build a model that predicts whether a new example falls into one category or another. It tries to maximize the margin around the separating hyperplane through a quadratic programming problem, and was first described by Vladimir Vapnik and Alexei Chervokenkis in 1964. Okay, next we'll talk about another kind of supervised learning called the decision tree. And a decision tree, you can think of it kind of like a 20 questions kind of game, right? So, and you can see from this picture, suppose we want to identify a picture of a car, right? So you might ask, is this thing alive? And does it fly? No, it doesn't fly. And is it something that can carry a lot of people? No, it's not. So at the final leaf, it's a sort of object that it's not alive, it doesn't fly, and it's not a big sort of vehicle that can carry lots of people. So it's a car. I'm trying to identify a car. So decision trees go from observations, the branches, to conclusions about some sort of item. The leaves, they're used in statistics, data mining, and machine learning. And they're good with targets that have discrete sets of values such that they're amenable to these sort of decision tree yes/no 20 question type things. Okay, and next we'll talk about semi-supervised learning. And a really popular kind of semi-supervised learning is something called a GAN, a generative adversarial network, where basically it's kind of like I have two AI networks facing off against each other, right? So I have one generator network whose purpose is essentially to create a sample of what the discriminator is trying to do. So in this example, maybe I'm trying to discriminate between faces of dog faces, right? And the one AI might try to generate dog faces to try to fool the discriminator, and I take real dog faces and then I feed it into this discriminator in order to train it. And with each pass, it gets better and better. It's able to detect the fake faces against the real ones. Now, the benefit of this kind of approach is that rather than having a lot of labeled data, I can provide some labeled data, like I can provide some subset of things that I know are dogs to the algorithm. But I can also have another algorithm generate data for it. So this helps speed up the process of learning. So it was developed by Ian Goodfellow in 2014, where two adversarial neural networks, a generator and a discriminator, face off against each other in a zero-sum game, and the network's trained by evaluating inputs in an unsupervised manner. Okay, next we'll take a look at something called a self-trained naive Bayes classifier. Now that's a mouthful, but as I describe it, hopefully it'll be easier to understand. And one good example of this is trying to find spam email, right? So if I have a set of spam email and a set of normal email, the probability of a spam, let's say, is 3 over the total in 9, and the probability of normal emails are 6 over 9. But we know through analysis that certain words are more likely to appear in normal email. So like we observe as we look through and process data that's normal. So again, this is semi-supervised. Maybe I help the algorithm along by saying, hey, these 6 emails are normal email and those 3 are spam email. So the algorithm can look and say, well, what do I see in common among those things? Well, dear and love, and maybe let's have a discussion at lunch. Those are very common words that are used in normal emails. But imagine like those scam emails from the Nigerian prince, send me your bank account and I'll give you $1 million in your bank, right? So words like million and dollars and bank, they might be used in normal conversation, but they're really likely to be used in spam emails, right? So, and you might use the spam emails also might use discuss or dear, but they're much more likely to be used in normal emails. So that's kind of what Bayes' theorem is all about a priori knowledge, right? Given some event has already happened, X, what's the probability that some new event, H, will happen, right? And there's just a statistical formula to figure that out. So that this naive Bayes classifier algorithm is essentially an algorithm that's utilizing Bayes statistics, given some a priori knowledge that these words are, the dear, love, discuss, and lunch are more typically used in normal emails. That helps me classify these things into spam and non-spam. So the method is naive because it doesn't consider the ordering, just the appearance. So I'm not looking at specific orders of words. I can bunch them all together, and I'm simply just looking at words. So I don't necessarily care that $1 million follows each other, just that they're in the histogram of all the words that are there. So this is a self-training method that trains on data by probabilistic statistics, namely the Bayes theorem, to classify data sets to be analyzed, and it's supervised, semi-supervised because it trains on some known sample data. Okay, so the last category for reinforcement learning, now this is the most complex, so it's probably the hardest to wrap your head around. It's the most complex you see from an equation standpoint, but I'll try to explain it in down-to-earth details. But think in your mind again, when you think or hear about a reinforcement learning, it's kind of like a mouse running a maze, right? You have a digital mouse running in a maze, and it's there's some environment that it's working in. There's some environment that it's working in, and I have some sort of agent, like in this case, a race car or a mouse trying to get somewhere. I observe where I am, so I'm rounding a corner and so forth, and how am I doing against certain rewards? So am I staying on track, on this track in this example, or am I getting closer to the cheese, right? So I have some states that maybe represent the states of the track or the maze, and some action I can take. I can go left, right, and stop, go slower, go faster. And in this case, it's a model-based learning. It's a markup decision process. And a Markov decision process simply means that it follows a state machine, right? So you distinctly go from one state to another. It's a dynamic programming, can break down the problem into smaller subproblems, and utilizes a Bellman optimality or recursively optimizes that subproblem and has some sort of policy and value iteration. So, and that's sort of represented by this equation. Okay. And then last, we'll talk about Q-learning, which is another kind of reinforcement machine learning. And again, it also has the same sort of paradigm where I have some sort of environment, I have some sort of agent, it has some sort of observation, I can take some set of actions, and I have some sort of states. The state at time t equals 0, say like right now, time t equals +1, say a minute from now, and time t equals t plus 2, say 2 minutes from now, right? And maybe Mario is jumping, so he has, think of the controller things, he can go left, right, jump, the little controller buttons you use to control Mario are pretty simple, right? There's only so many buttons and so many things you can do. And the AI takes those actions. So these are the set of actions that it can take. And based on what it can capture his position in XY and where the little enemies, these little, I guess they're mushrooms are, so the screen state is the states. So when he jumps, when he moves left and right, things happen. And the rewards are those little coins that when he hits something or gets something, he's able to get points, right? Or think of like a chessboard. The actions are that I have available to me are the current pieces that I can move, right? So like I can move the rook, up one of these 4 squares, or the left and right. Those are the available actions to me. And the board state, the states are the states of the board right now. Where all the current pieces are. The reward is I'm trying to capture the opponent's. I'm trying to win, right? I'm trying to capture the opponent's king, or maybe I might be counting points, right? Like how many am I up, material up in advantage, and then observations are I can observe what from my move what happens given the response to my move. Okay, next I'm going to talk about a large language model. And here this helps illustrate or helps your understanding, I hope, of a neural network, right? So large language models use deep learning to analyze text data to understand and generate language and train on diverse data sets to predict and produce text. And I'm just going to go over some key concepts and some key ideas that are used in modern large language model things. So in 2013, Google had a project called Word2Vec, and that was maybe one of the most pivotal insights into which really was able to kick off the LLM revolution, right? And their insight was basically, let me start the insight with an analogy. So, if I give you a map of the world and I say, if you're in, say, England, you can, and I see, where's London, or you can see that England has a close proximity to London, or Paris has a relatively close proximity to London, but has a far distance to, say, Washington, D.C., right? So the idea here is Google's insight was that we can represent words and give all the words a number. And from that number, or set of numbers, in fact, a vector, I'm able to calculate a distance to other common words that are associated with that word. So that's a really, really non-obvious and really powerful concept, right? So say maybe man and woman are often associated together, or king and queen are often associated together, or certain words like, I don't know, dog and cat might be associated together, or carrot and stick. They're able to give words numeric representations such that you can calculate a distance between them. So this concept of a word vector is really, really fundamental to a large language model. So next is context. Now, words often have multiple meanings that are based on context, and humans kind of easily understand that, and we can decode almost, without thinking, the context based on what something is said. Now, sometimes we can't, so we might need to ask for clarification, and that's where a lot of times where we get into arguments or misunderstandings can happen. But word vectors are used to help determine the meaning and the context. So, for example, if I say like time flies like an arrow, but fruit flies like a banana. So I use the word flies in both of these parts of the sentence, right? Like, but you know that time flies, like that phrase, time passes very quickly. But when I add the word like an arrow, now what's interesting is that now your initial were thinking of flies, meaning like it moves very quickly. So time flies. But as soon as I add the word arrow, it becomes a little less clear because now I'm talking about something moving through the air, right? Like an arrow moves through the air. But yet when I put all those together, it still kind of makes sense, right? Like time moves in one direction, arrows move very quickly and speedily from point A to point B. But then I say fruit flies like a banana. So here, of course, I set the stage for an arrow flying through the air, and of course, fruit flies. Um, fruit, fruit doesn't normally fly, right? Like an apple doesn't normally fly. However, fruit flies do fly, right? Like the little insect, fruit flies do fly, and they fly like a banana. But that doesn't quite make sense, but yet the whole thing kind of makes sense, and it's a joke, right? So put together, we can understand the context, but this might be very confusing for an AML thing to understand because you have to understand a lot of context behind these things for this joke to make sense, right? Or consider the sentence, flying planes can be dangerous, right? So here, does flying like a pilot who flies an airplane, is that dangerous? Or is it talking about a cohesive unit flying planes like a Boeing 747 can be dangerous, right? And so in context, we'll know what these mean. And that's what that's what these word vectors with context can do. So next, there's what are called transformers. Now, transformers is just in the neural network terms, it's a layer, right? So like we talked about the different layers in neural networks. A transformer is simply a layer. And what does that layer do? Well, it does a whole bunch of different things. But I showed you two simple ones. So one is to figure out context and meaning. So in this layer, this layer is just simply trying to figure out what are the verbs and nouns, right? So wants is a verb. So in the sentence, John wants his bank to cash the check. This first layer, maybe all it's doing is trying to find the verbs, right? It's just trying to identify what are verbs. And then the next layer is maybe trying to add another layer to the meaning. And so layer by layer, I'm decoding and breaking down that larger problem into smaller pieces, and that each layer can figure out something else. So what's important to note is that there are basically layers in a neural network model, and that each of those layers is called a transformer. So in the transformer layer, there's also something called an attention step. So it's sort of like a focus in a layer, and I usually have some sort of objective for that focus. So maybe I'm trying to match not pronouns with nouns. I might be trying to resolve homonyms. I might be trying to link two-word pairs. So each you can think of an attention step as like a matchmaking service for words. In the one sense, I'm seeking words that have a relevant context with what I'm looking for, and each word has a checklist for example, I see that I have a word his, a pronoun, and the query vector is I'm looking for something, right? Think of a matchmaking service. I'm looking for, so I came across this word his. That must mean because that's a pronoun, that must mean there's a male person in the sentence that I'm looking for. I also have something called a key vector, which can describe my own characteristics. Maybe somewhere else in the sentence, there's John, and John describes himself as a male person, right? Now, ChatGPT has, and ChatGPT 3 and 4 have over 100 layers with different attention objectives. So you can see, I'm just describing the very basic concepts here, but it can get, it gets very, very complex with all the nuances of what their layers may be doing. But I'm just trying to describe the basic ideas here. So there's something called a feed forward step where each word kind of thinks about the information that it's gathered in the previous attention steps and tries to predict the next word. So here we have these, I have the input sentence and the output vector. In other words, remember we talked about vectors. So what happens is I change what's very interesting is that I can have multiple sets of numbers that represent each word. So for example, bank might be 101, but here I might have given it a different number, like 106. That's still a bank, but in this case, a bank means a financial institution as opposed to the verb, like, I banked some money into the bank, right? And so I subtly can change the word vectors based on learnings in the transformation, and that's what this is talking about. So basically, each word, basically, as it gathers more knowledge about itself, it updates these word vectors in these hidden layers, and the output layer, the output thing, is the changed word vector. And then finally, we talked about backpropagation, where basically I go back and adjust those weights of the neurons, and as each output is analyzed, I walk backwards through the neural network and use matrix calculation to estimate how much I need to change each weight in order for it to work properly. And so these are some example layers or stages of a large language model. There's lexical analysis, syntactic analysis, and semantic analysis. Now, you as a human also do this too, right? Like we have some understanding of words, the lexicon. We have some understanding of those words in syntax, some syntax in the language. And those have some meaning, right? So there's lexicon, syntax, and semantics are all part of understanding English. You're able to understand me because of these three stages. And then discourse, I'm talking about something, discourse integration, and pragmatic analysis, where I'm analyzing that discourse in a larger, bigger picture. So that's a whirlwind tour of a large language model and how they work. And so let's summarize real quickly. So we talked about artificial intelligence. We talked about that there's narrow ANI, AGI, and artificial superintelligence. We talked about machine learning and how there's various kinds of unsupervised, supervised, semi-supervised, and reinforcement learning. And there's lots of different methods. I don't have the time to go into the deep learning, but like convolutional neural networks, transformers. We talked a little bit about transformers, Boltzmann machines, and deep belief networks. So that's a quick summary of these major areas of artificial intelligence. So next we're going to talk about a little bit of the key milestones and history, the past, present, and future of AI and its milestones. And we'll talk about some of the big developments that have happened over time and some recent developments. So in 1950, Alan Turing proposes the Turing test as a measure of machine intelligence and what does it mean to be human. Something can be seen as intelligent if you can have a conversation with it and that's indistinguishable from a conversation with a person. Now, you'll observe where essentially, things can pass the Turing test today, right? Like you can have a smart enough, advanced enough natural language generation and natural language understanding and natural language programmed thing to basically pass the Turing test. In 1956, John McCarthy coins the term artificial intelligence at the Dartmouth College Summer AI Conference. And in the 1960s, Ray Solomonoff uses Bayesian methods for inductive inference and prediction for probabilistic inference and machine learning. And we touched on this. So remember, what's the probability of the event H happening, given that I've already known about the event E has already happened. And so we see the foundations of a lot of even what we use today are really rooted in work that was done decades ago. 1965, Alexei Ivanenko makes the first deep learning multi-layer perceptron trained by gradient descent. And here we encounter the first of 3 AI winters from 1974 to 1980. So an AI winter is basically a period of time where people's expectation of AI was too high, and AI wasn't able to promise, wasn't able to deliver what people were hoping it was promising, right? So a tremendous amount of effort and research and money was poured into AML, but at that time, computers weren't quite powerful enough to accomplish some of the hyper miraculous things that people were overhyping it at the time, and so AML kind of fell out of favor, and it went into sort of a recession period. In 1980s, backpropagation, we talked about backpropagation. Algorithms spur resurgence in machine learning, which are used to iteratively train a neural network to gradually minimize errors. And we see that still as a common means that, we have certain weights of these various layers of a neural network. I look at the output and I can backpropagate and change the weights as I learn. So from 1987 to 1994, we experienced a second AI winter. And computers, bear in mind, computers all throughout this time are doubling in power every 18 months from Moore's law. And we are just in the PC revolution, so computers are getting more and more powerful throughout this whole time. But again, it's overpromised and underdelivered, and so we fall into another AI winter. In the 1990s, the shift from knowledge-driven approach to a data-driven approach through support vector machines. We talked about support vector machines on recurrent neural networks become popular. And in 1997, Deep Blue, a chess machine, defeats the then world champion Garry Kasparov, and it's used to symbolically AI is used to represent chess. In 2002, iRobot's Roomba is an autonomous robot that vacuums the floor while navigating and avoiding obstacles, and it heralds the domestic use of AI and robots. And this is really quite a milestone because an environment in a lab is one thing, but your home environment is an entirely different thing, right? So having something that autonomously runs around your house and has to interact with kids and dogs and pets and all sorts of various things on the floor is really quite an achievement. In 2005, Honda's Asimo robot is an artificial intelligent humanoid robot. It can walk as fast as a human. It can walk up and down stairs. It can deliver trays to customers in restaurant settings. You see here it's pouring a drink. It's really quite an amazing thing for 2005. In 2010s, deep learning becomes feasible, which leads to machine learning becoming integral to many widely used software services and applications. And in 2011, Amazon introduces the Echo, a voice-controlled intelligent personal assistant service, Alexa. In 2018, Hiroshi Ishiguro creates Erica, the world's first robotic humanoid news anchor in Japan. In 2018, OpenAI introduces GPT-3, an autoregressive language model using deep learning, but it hallucinates. And then, of course, ChatGPT then kind of explodes on the scene, reaches 100 million users, making it the largest consumer application. It's able to score 1410 on the SAT, in the 94th percentile, 163 on the LSAT, 298 on the Uniform Bar Exam, and it's multimodal. So it's right around here, maybe 2022, 2023, that ChatGPT really, the AI just kind of explodes on the social consciousness and explodes onto the scene. Everybody's suddenly talking about AI and how it's going to completely revolutionize. It's much more palpable to the I'd say average person. So I've been giving this lecture for years and honing and refining and constantly changing this set of lecture notes over the years. And so I went from kind of talking about autonomous self-driving cars to then in October 2023 to sitting in an autonomous self-driving car. I used Waymo in Phoenix, Arizona, and it was quite an experience. It was very interesting, and we'll see, I think, more and more autonomous self-driving cars as time moves forward. So AAML, it should be driven home that even though the previous slides show big, huge, major milestones, a lot of things aren't necessarily, they weren't here and suddenly they are here, right? But rather they're kind of gradual. So we'll see a lot of these things are gonna be here for the next 10 years, let's say, right? Like many of these things are things that have been in development for quite a long time. They're making some of these things that to various degrees are making some splash in the news, and they're going to get better and better and more pronounced over time. So autonomous AI agents, that's the kind of latest thing in the 2025, I would say. AI agents, if you're tuning into the AI news, that's kind of all over the news, let's say, quote unquote. So AI systems that can perform complex tasks independently, boost productivity and automation. And there's different kinds of AI agents that do different stuff, goal-based, model-based, reflex, utility-based agents, learning agents, multimodal generative AIs that are able to handle multiple data types like pictures and words, video, that enable richer content and applications. Human-centric and explainable AI, so a focus on transparency, bias mitigation, and ethical AI practices is really important and crucial. The fifth generation of wireless technologies with massive machine-type communications and the Internet of Things. So we see here the basic layers of the Internet of Things, where I perceive something, I transport that data, I process it, and then I have smart applications that use the IoT. And then extended reality, so augmented reality, mixed reality, and virtual reality will be make its way into our lives. AI in healthcare and biotechnology, we'll talk about that more, but enhanced diagnostics, telemedicine, and drug discovery, and AI enhanced creativity. So this is also kind of making a news as AI starts to dip its toes into creative things, making music or poems and such. But these are just really, AI is really starting to, I would say, kind of explode, right? So this is just a slice of some of the things that are going on. It should be noted these aren't all the major things that are happening, but these are some of the kind of more interesting areas of research and prominence. Also, I think it's kind of interesting is so about 6 years ago or 10 years ago, when You Look Like a Thing and I Love You was written, it was interesting to note that the number of neurons there. So the book talks about the network of the time, right? And the network of the time in 2019 was 0.96 million neurons, so about the size of a wasp or bee's brain. Today, though, the Intel Neuromorphic Hala-Point AI system in Sandia National Labs has 1.5 billion artificial neurons with 120 billion synapses in 140,000 neuromorphic cores and consumes 2,600 watts for 20 petaops, quadrillion operations per second. And it's about the size of roughly a capuchin monkey cortex or an owl brain, right? So that's about roughly where we are now. And that's just in 6 years' time. So, another 6 years, I don't know if it may not go at that same progression, but it's really impressive how fast we're moving, I think. So here a little bit of prognostication, and it should be noted that this is very much take this with a grain of salt. I looked at I did some research on but these are people also, how good is a prediction? Your guess is as good as mine. So stage one is we're kind of in this area of machine learning. There's bots and Siri and Alexa, Cortana. We use it's user-driven big data models for machine learning. Machine intelligence is starting to get into this now with trained ad hoc models and custom learning, and then eventually machine consciousness. So in the next 10 years, we'll see more and more and better enhanced scenario AI capable of more than one task, with each task designed to be able to be performed with specialized functions. Maybe by 2030, AI-initiated operations to do art, software, mathematical solutions, and research papers that are initiated by AI programs. And then some decades from now, we'll have really truly artificial general intelligence AI with full cognitive capabilities mimicking a human. And then eventually, super intelligent AI that's cognitive, that has capabilities beyond a human. It's conscious, it's sentient, and it has a conscience. Okay, next, we're going to take a look at some practical applications and some areas where AML is used. And we talked about a lot of the ML algorithms, and I created a sort of summary slide of where these algorithms really work well in. Not every algorithm works uh, uh, well in every kind of task. There are some algorithms that are much better suited for certain activities, right? So for unsupervised learning, the Apriori associations are good for sales functions or word associations, like word searching sort of things. The k-means clustering, remember you're looking for groups and clusters of stuff, is good for performance monitoring or searching intent. Artificial neural networks are great for generating new synthetic data or data mining and pattern recognition. Supervised learning and linear regressions are great for sales forecasting. It's projecting through mathematical things or risk assessment. Think like insurance, assessing risk for insurance purposes. Support vector machines are great for, remember, it's using those hyperplanes to divide groups of data. New data points that come in fall into one or the other side of a hyperplane. And so those are great for image classification and financial performance comparison. Decision tree classifications, again, think 20 questions, right, are great for predictive analytics or pricing. The semi-supervised learning, where I have the generative adversarial networks, the two AIs that play off against each other, might be good for audio and video manipulation and data creation. The self-training naive Bayes classifier is great for natural language processing. The reinforcement learning, I think the mouse running through the maze, the digital mouse running through the digital maze, are great for linear tasks or estimating parameters, and Q learning for policy creation and consumption reduction. Now, AI/ML is really going to touch probably every area of our lives, but it'll happen at different rates, and it's not likely to be something that wasn't here at all and then something it's everywhere, right? It's going to be a gradual infusion into our society. So, think about computer chips, right? Computer chips developed in 1947 with the first point contact transistor by Shockley, Bardeen, and Brattain. The transistors slowly showed up in society, right? In Walkman radios, and eventually in computer chips and integrated circuits, and now they're kind of everywhere. We don't really think about them. The same thing will happen with AI, I feel. So it'll be in just about everywhere, but it won't necessarily be taken up at the same rate everywhere, right? So, and it'll have an appearance in different areas, and in different means and forms, and it will touch different industries differently. The more digital, the more electronic the form, the faster the uptake, right? So like in e-commerce, maybe in the aerospace industry where you're booking, especially where you're booking like flights. Think hospitality where you're booking a lot of, I'm looking for a particular hotel at this particular distance. I'm flying to Japan in a couple weeks from now, and it was a very manual search to find the right hotel in the right place that's close to where I want to be for the right price, and blah blah blah. I had to go through a lot of hoops, and that's an example of where AML could help a lot. Real estate, so imagine taking like a virtual tour through a home, right? In agriculture, the Internet of Things, where I have lots and lots of little sensors deployed on a field, can help me monitor how my crop is doing. Industry 4.0, we'll talk about this more. The smart factory, able to dynamically change and reshift itself, managing inventory. The defense industry, now this one in particular, especially for the law, maybe, it's an interesting one because you probably don't want to turn over the nuclear keys to an AI system, but think of a drone, right? Drones and electronic warfare are certainly a thing where AML will play a role, and maybe perhaps a scary role, but that's something where it'll also touch. Banking and finance we'll see sooner rather than later because a lot of it's all digital, right? So we'll see AML play a large role there. Insurance, so for actuarial purposes to figure out statistics of how likely you are to get into an accident or how likely you are to die in something or some activity. The ride sharing, the robo taxis we've already seen. And here, of course, you'll spend many more courses, many more lectures on the legal aspects of AAML. Communications, this is my area, so in telecommunications, AAML will certainly play a role from all sorts of different areas, from the massive machine type communications and IoT we talked about, to URLLC and haptic communications, to 5G and 6G and beyond. So right now we're entering the era of the 6G research. So we're starting to propose, and many companies are proposing things for 6G, the next generation of wireless technologies. And one thing that I've read and attended and listened and watched to dozens and dozens of 6G research papers and presentations. And one thing is for certain, 6G will have there's a lot of things that people don't agree on, but two things I see recurring are 6G will have sustainability baked into it. So a lot of things about energy savings and being greener and being sustainable. And also it'll incorporate smart and AIML type things. The smart city, and we'll see a slide on this in a bit, smart AV applications and social media, of course, AIML has already played a role and will continue to play a role in politics and government. And at a more personal level, entertainment and smart entertainment, your workplace. We talked about AA agents and smart personal assistants and your digital twin. In sports, now here, because this is a more personal thing you do, like running or jumping or tennis or skiing or whatever, here probably it's more like monitoring your health and your biosigns and things, right? Smart homes, we'll see that in a second. Healthcare applications, gaming, of course, that's all virtual and digital, right? And then education and learning. So in your smart home, there's all sorts of ways that smart robotics and AML will play a role, from security monitoring to environmental control to entertainment to informatics, like think Echo, Alexa, profile execution, AV, like when you walk into a room, it turns on the music that you like. Energy management, smart energy management when you're away, turning down the lights and the temperature. Safety management for home security. Telecontrol, being able to remotely operate your house from afar. Appliance control and lock and security. A smart city, we're only really just starting to, not even really just starting to see some of these things, but your the city infrastructure will become much smarter in the next 20 years, right? So emergency services and power management, disaster recovery, public safety, public transportation, smart parking, augmented reality. Imagine walking down the street and plugging in your landmarks can talk to your phone and tell you, hey, this is something special, or your AR glasses can tell you this is something special. The Internet of Things, connected car services, the city that can talk to car, redirect traffic, help you find parking, sanitation management, transport analytics, and water management. Now there have been three major epochs in industry, right? Three major revolutions in industry, and we're entering this fourth one. So Industry 1.0 was just about basic mechanization, steam power, the weaving, the loom. Industry 2.0 was about mass production and the assembly line. Industry 3.0 was about automation, computers, and electronics. And Industry 4.0, which will be fueled by AML and 5G, the cyber physical systems, and the Internet of Things and advanced networks. So being able to monitor safety, assembly line management, just-in-time management, enterprise resource planning, cyber physical systems, the Internet of Things, and machine-to-machine communications, RFID controls, factory security, robotics, programmable logic controllers, and manufacturing operations management, and supervisory control and data acquisition are all going to feed in to create the next smart factory. So last, we'll talk about some of the players. In a prior lecture to this, I had just kind of this huge landscape of players. So just to note, I've taken that slide out since then, but just to note, there are like dozens and dozens and dozens of AML players, right? So just bear in mind there's many players in the AML space that are all looking to do interesting things, and these are just a few of the maybe bigger players, right? So Microsoft has the Project Oxford, Cortana, IBM, Deep Blue, and Watson, Amazon, Alexa Voice and Echo, and Amazon Machine Learning, Salesforce, Tempo, and Salesforce IQ, Apple with Siri, Perceptio, Emotient, and Vocal IQ, Facebook with M and Deepface and Fair, Google with TensorFlow, Google Now, and Google Brain. I watched a lecture of kind of where AI is going with Google, and they had a really interesting. It was a really interesting lecture. And so it's talking about like AI for social good, to help with disaster recovery, and to help save the planet, and personal healthcare monitoring, and AI in the creative space with Party and Funaki, which are like language, image, and video generation tools. And AI for language translation is Google Translate is widely used, but they admit, there's still many languages they have yet to bridge. Microsoft's doing a tremendous number of things as well. They break things down into this innovation sandbox, business scenarios, AI for society, autonomous systems, and secure responsibility. And these are, again, just a small slice of things going on right now in 2025. So I picked a couple of what I thought were quite interesting things, but note there's many hundreds of other interesting things happening in the AIML space. And it's definitely growing, right? So like several years ago when I sort of started doing these lectures, it was easier. Let's say there's a smaller set of sort of very interesting things happening, and now there's a lot of very interesting things happening. So GNOME by Google DeepMind is an AI tool that identified 380,000 new materials at low temperatures, which could be revolutionize energy, material science, and processing power, potentially leading to better solar cells, batteries, and superconductors. And if you know anything about materials engineering, the search for new materials is long, laborious, hard, and difficult. Maybe there's only 118 elements, but you can put those atoms together in a bazillion, almost near infinite different number of ways. And so that is a really good application of AI, right? Being able to try lots of different things virtually, and from there it can find new and interesting materials. Brain-computer interfaces, so deep learning-powered devices that interpret brain signals to enable control of machines and communication for people with disabilities. And this technology is advancing towards practical human-machine collaboration through thought. So think of those things that where somebody's handicapped, for example. So you can use this brain-computer interface to help steer to help steal a wheelchair, or help somebody write, or speak, or overcome some of their handicaps. GraphCast for climate prediction, an open source ML model that predicts weather conditions with superior accuracy and speed, including cyclone paths and floods, enhancing disaster preparedness. And then, of course, robotaxis we've already talked about several times. So fully driverless taxis have moved beyond the beta testing and are now being rolled out in cities worldwide. Zoox and Waymo are examples. Another company is called DeepGram, and this slide is dedicated to some new companies that I found that I thought were kind of interesting. But again, note there's many dozens of more, and many interesting companies all doing lots of interesting stuff. But these are a few examples that I found that I thought were interesting. So DeepGram is a multilingual transcription. It's a voice AI platform providing APIs for text, speech to text, text-to-speech, and full speech-to-speech voice agents. They're developing a speech recognition platform with high accuracy and multilingual transcription. Snorkel AI is one about, it's a company dedicated to data labeling. So we talked about how in supervised and unsupervised learning, I have to go and label. This is a picture of, laboriously go, this is a picture of an orange, this is a picture of an apple, this is a picture of a cat, this is a picture of a dog. So Snorkel AI is pioneering the shift from manual data labeling to programmatic data development for AI. It empowers enterprises to use their proprietary data to build specialized AI models faster and cheaper with applications across domains and sectors. Juganu is basically digital twins for retail. It leverages lighting and infrastructure to provide a wireless computer vision and advanced services for connected for a connected environment, smart fixtures, using a network of sensors to feed data into a computer vision brain that transforms spaces into a data ecosystem. Oransa is a drug discovery AI native biopharma with AI platform that harnesses available human disease data to discover novel therapeutics and raise the standard of care. It harnesses abundant, available, and heterogeneous human disease data to discover novel therapies. Now, for these four, I kind of went to all of these websites and like you can see here, for example, I basically took some of their own, the company's words that they describe themselves with and kind of put them into the description on this page here. So, so again, I mentioned that the place where I work in Murray Hill, New Jersey, is the headquarters of Bell Labs, and I'm the photographer for Bell Labs. We just recently had the 100th year anniversary of Bell Labs, so that was a really interesting set of events. And we had Eric Schmidt, who was the former CEO of Google and a former Bell Labs intern, talk. He gave a talk, and that was a really interesting talk. He talked about a bunch of things, but one of the things he talked about regarding AI ML was that AML is kind of a race, right? We're in a race with other countries, with other companies, and where the developments are that when we hit certain milestones that are really major, like think of what's called the singularity. When we first hit that, when we go from ANI to really AGI, or we go to from narrow to more general intelligence. The people who can make some of these milestones are really going to have really quite a big advantage, right? So, and he talks about time is even a 6-month difference can be an exponentially powerful thing. There was another talk at the Bell Labs 100 celebration, which was had Stephen Chu and Horst Sturmer, Robert Wilson, Nobel Prize winners. I've never been in a room with so many Nobel Prize and Turing awardee winners. Now the Turing award is kind of like the Nobel Prize for computers, right? And Aho is there, and Jan LeCun, who's like the grandfather of AI and the godfather of deep learning. And he was talking about basically right now we're going to see like a importance in partnering with human. The next big thing he thinks is partnering with smart applications and algorithms that really will enhance our own capabilities to be more productive and to do more and to partner with humans to make them more productive and more capable. So think like kind of like your eyeglasses let you see better, or a calculator and your smartphone lets you compute things. You could do that by hand, but it really enhances your mathematical capabilities, for example. And the same thing, we'll see lots of technologies that are smart applications, which will let you plan better, will make you able to monitor your own biosigns easier, or if you're a researcher, to be able to research better and those sorts of things. Okay, so what have we learned? We'll end with a summary here. What are some of the biggest ideas we've learned? So I talked about artificial intelligence, and we talked about how we're really kind of in this era of artificial narrow intelligence and problem solving, and artificial general intelligence, which we're starting to dip into now. So think like robotaxis, where they have something that's capable of essentially a huge collection of artificial narrow intelligence things that it can solve problems on the fly or navigate environments, and eventually artificial superintelligence. Machine learning is machines that learn through experience without explicit programming. So we talked about lots of different kinds of machine learning algorithms and methods that are divided into 4 major categories: unsupervised learning, supervised learning, semi-supervised learning, and reinforcement learning. And I didn't talk too much about deep learning, but note that there is a whole area of learning that's called deep learning, that uses artificial neural networks that can adapt, learn, and make intelligent decisions, of which convolutional neural networks and transformer layers and Boltzmann machines and deep belief networks play a role. We talked about the basic framework of how AML works. So if there's one slide I want to leave you with, it's probably this one. I took a deep dive into a lot of things, but you should burn this slide into your mind, right? So that basically all of AI fundamentally right now for artificial narrow intelligence and heading into artificial general intelligence works by training data using a smart algorithm to evaluate and deploy and feedback and seeing how it's done. It defines some sort of problem to solve, collecting data, and maybe massaging or cleaning or formatting that data and taking out bias. And then it trains the algorithm. The algorithm can detect and find and observe key features and characteristics and patterns from that data. There's some sort of core algorithm. We talk about a bunch of different machine learning algorithms. And from that, it has a resultant model. So it starts with maybe a model with some maybe random settings, but eventually this output model becomes more and more refined. We talked about the 4 different kinds of supervision. And ultimately, AML is useful to us because it's doing something, right? It's either helping us or coming up with some prediction or making some decision, or and it's doing something, right? So that algorithm has some sort of meaningful output to humans, right? And so and it might be wrong, it might hallucinate, it might make a poor decision, it might get that image classification wrong, and that's why it uses evaluation. It sees how well it does against the targets, or there's some way to evaluate, how close is it to the end of the maze, and it feeds that back into the algorithm to become better and better. So with that, I'm gonna say thank you for your time and attention, and I hope you walk away with this with some better understanding of AML. And we'll stop here. Becca might have a question or two that we can entertain. That I'll entertain.
I had a couple that I wanted to ask you about, some things you talked about during the presentation, and the students could benefit from a little more information on. So one is you talked about computer vision, how it's something that's really easy for humans and really hard to teach computers to do.
Yeah.
Can you talk a little bit more about that, sort of the
Sure.
idea that there are some tasks that are really easy for us that are really hard
Sure.
for AI?
Yeah, that's an excellent question. So maybe we'll go back a little bit in the history. One thing that we've learned through time is that things that we thought were extremely difficult, such as playing chess, turn out to be not so hard for AML. And some things that we thought were somewhat easy, like speaking and seeing and walking from across a room from point A to point B, are actually quite difficult in the 1990s and early 2000s for computers, right? And why is that? Well, so the more rules based and the more narrow, the more confined the problem space, and the more well defined the problem, the easier it is for AML to tackle the problem. Now, chess still has it's a huge problem space, but it still can be tackled with just lots of computational power. What makes what makes navigating and computer vision, navigating a human actual real environment difficult, and computer vision difficult, that we take so much for granted, that is because our brains are wired to learn and interact with our environment. um, Now, I read a really interesting book this year called Sentience, and it talks about consciousness, right? Perceptual consciousness, and how we're able to learn, and how, can this just collection of neurons? If you just put a bunch of neurons together, will an emergent property occur such that you're just conscious? Like, can that happen? Um, and it describes how we can look at animals and the animal kingdom to see it asked that book asked a very interesting question. Are other things conscious? Do other things have a consciousness? And how can we tell, right? That's a really interesting question. And one of the really insightful things from that book that I got was that um, mammals and birds um, are very likely candidates for consciousness. Because one of the things we observe is that they have to essentially kind of train their neural networks, and we observe that many other animals kind of don't do that. But in the mammalian kingdom, mammals and birds, they have those two animal domain kingdoms, right? They do something that many other animals don't do, and that is they play. So, gorillas play and cats play and dogs play and birds play too. And why are they, why do we play? How does that really help us with our evolution? How does that help us survive? If I'm um, playing around and running around and we're boxing or playing or catching or whatever, how does that really help me survive? What it really does, the book argues, is that it's really training your neural network. It doesn't use those words, but I'm essentially using those words. So basically, it's helping you develop those. You have to train your networks, right? And we take that so much for granted now as adults. But think of a baby who's crawling across a room, who's learning how to walk and speak. It's essentially training its neural network, right? It's playing. And the approach to how would you write a program if you think about a line by line program, right? Like before neural networks, a line by line program of how would you be able to describe a picture that your robot is taking some kind of image of a room. Imagine that room has chairs and tables and balls and a baby and a dog. And it has to navigate without killing or running over into another object or tripping over a dog, the baby. And how would you do that? Like line by line, you'd have to say, in this pixel, do I see a dark spot, a light spot? Is this, are those collection of spots, digital pixels? Is that a table? So computer vision turns out to be an incredibly difficult problem. Much more difficult than we initially thought, at least, because of the complex play of light and the different kinds of sensors you might use. Now, today, decades on into this kind of research, we have lots of different kinds of sensors like LiDAR and so forth. Um, and but there are lots of things that make, if you study computer vision, it's a really interesting topic because, just as simple something as simple as a shadow is, how can you tell that's a shadow and that's not a shadow, or that's an edge of a road and that's not an edge of a road? It turns out to be a very interesting and sort of difficult problem to solve. And over the decades, lots and lots of smart people have designed different transformer layers and neural networks, one for edge detection and one to figure out this is a sign and so forth. So and I think it's the things that they have to solve are not so obvious immediately when you first think about it. And that's why perhaps, one of the first things like the Roomba was a really, really simple, it doesn't look anything like Rosie the robot, or a humanoid robot, an anthropomorphic robot. It's just a circular disc that if it bumps into something, and it does bump into things, that it turns around and tries to, go in a different direction. So
An example that you talked about with me before we were talking about this presentation and other presentations I've been working on is laundry. So teaching someone how to do laundry is a multi-step process, but as adults, we don't really think much about it. We just know what to do. But teaching a kid how to do
yeah.
it is a lot of complexity.
Oh, absolutely. I think one of the I've read a lot, and you and I both have read and watched a lot of AI, ML, books and movies and media and stuff and articles. And one of the things that that I recall, I don't know which book I read this from. Again, I read a lot of like this year I read 40 books, right? So I read a lot of nonfiction books. But one memorable sentence that I remember was that um, the a human being that can is a general machine that can do a billion different kinds of tasks. So that doesn't mean the task itself is easy or doesn't have much value. So imagine and why is for example I don't know, a waitress paid a lot less than say a brain surgeon, right? Um, I mean, and the book said, well, consider like a task of like carrying a plate of food from point A to point B, or making a cake, following directions. Um, the more the more ubiquitous that the people that can do that particular task, the more broadly that people can do the task, the sort of lower we tend to sort of value it in society. And but that doesn't make the task any less interesting or less complex from a I'm going to design a robot to do that task perspective, right? So now baking a cake, anybody can bake a cake. You just follow directions, put these ingredients in a bowl, mix them up, and pop them in the oven. Um, But however, for a robot to do that task, to break just something as simple as breaking two eggs into a bowl without the shells also falling in the thing, that's an incredibly complex and hard thing to do, right? Um, and we take that so much for granted, like something like doing the laundry, being able to just take a bunch of clothes and plop them in a cylinder, turning some dials and pressing a button. But the act of also folding clothes, I remember reading something about laundry as well. Like the act of folding clothes into a particular way with a robot is incredibly not obvious and not so easy, right? So the to optimally, now there are robots now that can do that, by the way, but it's also an interesting task. But also an example of algorithms to learn how certain clothes should be put together and or not, and what the mixture of certain ingredients. So there's three things that clean clothes, right? So there's agitation, heat, and chemicals. Those three things clean stuff, clean clothes. Um, and no, but there's also ways to ruin clothes, right? If you put bleach on on something, you can cause colors to bleed, on and your previously white shirt and now becomes pink or whatever. So so those sorts of things that humans learn to navigate the world are not so obvious to machines. What we would call common sense is not so commonsensical to a machine, right? It has to be somehow learned. We just kind of learn it just by going about living, by interacting with other humans, or by play, right? Through reading or through going through great K through 12 school. We learn what we call common sense, just rules about the world, of how the world works. But think of how, for a robot who doesn't know anything, it has to also do that learning, right? It has to also go through years of that sort of training, um, and to just even learn to use its own limbs, So I think sometimes we have too much expectation of, say, robots, and in other areas maybe where there's a particular problem is quite amenable to AML algorithms. Maybe we have there maybe it's underhyped, right? So there's areas where we're overhyped. I think there's other areas where we're underhyped. That by the way is the same thing that somebody asked Eric Schmidt. They asked, one of the questions they asked was, do you feel AI is underhyped or overhyped or just about right hyped, right? And his answer was quite interesting. He says, well, in some areas it's really underhyped, right? In other areas it's overhyped. So so there's some people, because we're influenced by science fiction movies and things, we expect maybe too much from AML. But in other areas, maybe it will be able to over deliver in the next few years, I think so.
Yeah, no, I think so. And I think that balance between what we should be using AI for, what AI is best at, and what AI maybe shouldn't be used for because it's not as good at it, or humans are much better at it, or
Yeah.
is a tough balance.
Yes, and I think this slide is a good kind of a good example of that. There's some areas where like a defense is a really good example, right? Like I'd be quite scared if AMO was in charge of our nuclear arsenal, right?
Yeah.
Like that kind of thing. And I'm sure you're going to explore lots of interesting legal aspects of AML. But one really good one and very simple one is the trolley problem in a car, right? So consider a self-driving car and the trolley problem at some point. suppose a car has to make a decision. I'm going to run into a tree, over a cliff, or hit this baby in front of me that just happened to jump right out in front of my car. And so, do I kill the driver and the passengers in the car, or do I kill this, the thing that just happened to jump out in front of my car, right? That sort of trolley problem is one and there's lots of I'm sure there's lots and lots of corner cases like that AML will uncover over time. But that one is, a simple one. That's a low-hanging fruit, like an interesting and problem to consider. Who's to blame? Who's at fault? And how do you tackle that sort of situation? How do you program for it? Right? So.
That's also why a lot of states require a driver for autonomous vehicles, because uh, most of the things are easy to train the AI on, but a baby randomly appearing is something that is a rare enough occurrence that, well, a human will know what to do. It's hard to train an AI on those rarer occurrences.
Oh, absolutely. Yeah, yeah. And actually, my so the next data point in the autonomous vehicle story of, like, I went from talking about, years ago, talking about in this lecture, in this course, talking about self-driving cars to in October 2023 sitting in a self-driving car, the Waymo, and there was nobody in the front seat. There's the passengers also weren't, you didn't have the ability to grab control of the reins if you needed to just last month, my neighbors got a Tesla Model Y self-driving car. So I thought that was, it's really interesting. But the way they've done it, though, is you still have to be able to grab onto the steering wheel and drive at any moment, right? So basically, it's self-driving. Yes, it can go from point A to point B, but you have to also be able to take control because of just exactly that, because the real world is so complex. And also, I guess it pays attention to, from what I'm told by my neighbors, they told me that, you have to kind of pay attention to, like, the car is watching you pay attention. And if your attention lapses, you get penalized. So you're not able to use the self-driving thing for an hour or whatever. So I thought that
Interesting.
that was a very interesting way to approach it.
And even cars that aren't Tesla Model Y. So my husband and I have a car, an electric car, and
Hmm.
the more modern cars now seem to have all kinds of features, like you're too close on this side, or you're too close in front, or
Oh yeah.
backup cameras and so on. And a lot of those don't use pure AI, but some of them use some machine learning and so on. It's interesting that we're seeing it adapt into more places in smaller ways.
I think
Talk
that's
about,
a
go
excellent
ahead.
point, because I think in every one of these areas, the smart partnership with humans you'll see before you see any sort of full AI in anything, right? Every single one of these areas, I think you'll see where and not even necessarily like a full AI ML or AI ANI thing, but just more, just even a simple just algorithm will partner with people to in every one of these areas, and I sort of walk through some of them, but to help us do stuff better. So I think that's definitely the first step that we'll see. That's that sort of gradual transition I talked about. So I think we'll see AML, not suddenly it wasn't here and suddenly it's everywhere. But one of the first things that I think you'll see is a partnership with people doing something smarter, for something either they already do or just facilitating and helping them accomplish something.
That's kind of how I encourage students to use AI as a partner to help them improve what they're doing. Because I don't know if you found this, but I have found with ChatGPT, etc., that if it's an area where I know nothing, I am less comfortable with the output than if it's something where I'm an expert.
Yeah, actually, I did I recently, a couple months ago, I did an outreach program to eighth graders at a local, me and some other colleagues from my work, and actually next week, in fact, I'm also doing an outreach to that same school, in Union County in New Jersey, because that first one was so successful. And one of the questions the students asked actually was, what are the dangers of AI, and what are for a grade school child, what are the dangers of technology? Um, and the way I answered that was, I don't think we should be afraid of technology. I think AI, ML, as with almost all other technology, is a tool, right? So like, there are very, very few technologies that are intrinsically harmful to people. They also asked, something about what's harmful what's a harmful technology. The only real harmful technology, I feel that like you could just completely remove this technology, and it would kind of make the world a better place, is nuclear weapons, right? That was my answer to
Yeah,
that.
that's
Um,
fair.
and I said, I mean, even a gun in the hands of a police can help save lives, so there are very few technologies that are just purely positive or negative. It's kind of what you do with it. And so um, the answer to one of their questions was, I don't think you should shy away from AI/ML. I don't think you should shy away from technology. Rather, you should learn more about it to see how it can be misused, or how I might accidentally misuse it. And I think the more knowledgeable you are about, the use of a particular technology, the less you'll be afraid of it, and the less you'll misuse it. And also the more you'll see how it might be misused by others, right? So I think understanding technology is really what the more proper question is, answer, or approach, I think, is just to learn about, not avoid what technology should we avoid, but where do I lack some knowledge in something, and how do I learn about it better more?
I think avoiding over reliance also, because you won't always have it with you. And so you still have to learn something. You still have to know how to do things without the AI so that you can evaluate whether the AI is doing what it's supposed to be doing.
Oh, absolutely. Yeah, yeah. I have lots of great stories related to that with navigation, for example. Um, I had
Oh, yeah.
a I had a friend whose niece and nephew were navigating from Texas to New York. And my friend Freddie, she called them like, "Where are you?" And the kids were like, "I'm not sure." And they were just blindly following the directions on the navigation system. And it turns out that they were like 2 hours off because the navigation system got confused, and they had no idea at all where they were, and had like, so over reliance on technology can also be a problem. You should at least have some fundamental knowledge of what you're doing, or look for other, don't necessarily look from one place for an answer, right? Like, what Aristotle said, be wary of the man of one book.
Yes.
Um, look, yes, double fact check, sometime AI, be aware that sometimes AIs hallucinate, and when an AI hallucinates, meaning that they'll tell you an answer, but that's not actually correct, they do it in such a way that it's like with really strong confidence, right? Like, this is the
Yes.
answer, and so you might accept that as, oh, of course, that was told with such confidence, and here's, all these references it gave, that it's got to be true. But it's not necessarily the true. I've already experienced myself several, an example of where I hallucinated when I was doing some searches.
A
I was
lot of
looking I
that's
was
right.
looking for the what's the um, most successful and most popular franchises, right? And it was kind of right, but not exactly right. So that was interesting.
Yeah, a lot of lawyers got in trouble for that reason.
Yeah, yeah, I can imagine. Yeah.
So with hallucinations, can you talk a little bit about why no one has solved the hallucination problem yet?
Yeah, so I think AI hallucinations are that's an easy question to ask, but a hard one to answer because of the different kinds of AI algorithms, right? So because there's so many different kinds of algorithms, they may all arrive at a wrong conclusion or wrong answer in different ways. So think of when I go through. Let me take a really simple example. So suppose I present an image sorting algorithm of a picture of a dolphin, and I ask it, is this a picture of a cat or dog? And it says, well, this is a picture of a dog, but wait, this is a picture of a dolphin. It's neither of the two, right? So it hallucinated. It gave you a wrong answer, but it can very confidently say, no, this is a picture of a dog. And it's because the way it's programmed, it's only looking for, certain answers, right? Or you've defined the problem in such a way that the answer maybe falls out of that problem space. And that's a very, very simple example just to illustrate the problem of AI hallucinations. But um, you know, the data that it's trained with can cause it to hallucinate. The how it's, its problem space that it's defined to try to solve can cause it to hallucinate. And any hallucination is really just saying, it had a wrong answer, right? But think of every epoch, every training cycle it goes through. There's going to be lots of wrong answers, right? There's lots and lots
Right.
and lots of wrong answers. So, and it gets better and better over time, the more data it's exposed to, and the less and less it hallucinates, right? So, um, and when you have something as complex as trying to understand all the nuances of human language and anything that under that, so somebody can ask about anything under the sun, and it's essentially training on the internet, right? It's training on websites and website data, and you found it on the internet, so it's got to be true, right? So, so the AI is essentially just doing the same thing. It's just crawling the internet for answers. And so, of course, the internet isn't always right. So,
So the students for their final assignment for this course are going to be training AI agents.
oh, neat.
Um,
Okay.
so they're developing throughout the course compliance documents, and then they're going to be training an AI agent so that the agent can answer questions from employees about their documents. So can you talk a little bit about AI agents?
Yeah. So, let me see where I have that slide. I was in the latest developments here. So, agents are one of the more recent, I would say, sort of areas of interest and hype and development. And it's really basically a focused AI thing to do something specifically, right? So maybe the simplest one is like a goal-based agent, right? It's an agent it's a AI program or model that is trying to solve some kind of problem. Or maybe it's an agent that's specialized to try to, like the example you gave, to try to learn through, to look at 10,000 documents and try to learn something. Or a reflex agent is one that that's trying to figure out answers to stuff, or utility ones which are trying to improve some sort of process, or maybe it's trying to perform some sort of utility function, right? So the basic idea of an agent is to essentially perform some sort of task, right? It's just a fancy name essentially for um, a program that's focused in trying um, to intelligently perform some sort of task. And usually they're structured in such a way, I think they're called agents, because essentially a lot of them, at least a lot of the ones I've seen, are kind of designed to kind of help somebody do something, right? So they're kind of like smart assistants. At least many of the ones I've seen. Now that might there's smart agents that do more than that, but but a lot of what I've seen are sort of think of kind of like somebody who's a helper. And imagine if you had a digital helper to do something, right? That's what a lot of these agents are kind of geared to do. And again, that it's that bridging step of that sort of partnership between human and AI activities, right? So I think this is a very promising, I feel, sort of stepping stone from to getting people to be more accepting of AI and what it can do, and gradually infuse it into their lives in a positive way.
So just two more questions. So the first one is, one of the themes of my course is balancing regulation and innovation. So an example, the Biden administration was more on the balance of regulation slightly. China would be an example of a place that's about innovation over regulation. So you talk a little about as someone who uses AI to develop things and knows more about that side, what your feelings are about that sort of balance between innovation and regulation?
Yeah, that's an excellent question. So I think like maybe if we take a different outside of AML, let's take an example where that balance kind of went off kilter, right? So like CRISPR technology. I don't know if you've heard of like CRISPR, but like
Yes.
uh, genetic technologies, right? So China, they were
Gene
gene
editing technology.
editing, yeah.
Yeah.
So like here, you know, some sort of rogue scientist went off and did some gene editing, uh, kind of outside of what would have sort of shocked the scientific community, because it was sort of outside of the sphere of the normal flow of things, right? So, um, so you know when you I think when you side too much on just pure innovation just for innovation's sake, maybe you can end up with sort of rogue scientists and rogue innovators that are maybe doing amazing things and pushing the boundaries, but maybe, you know, they're somewhat questionable to how they did that, right? So the ends kind of justify the means sort of thing. Whereas I think with what regulation does, especially in the terms of AML, is kind of now is the right time to think about how could things go off the rails, right? And before, like I described the trolley problem with a car, um, you know, uh, if and AI self-driven cars, unfortunately, have already killed people, um, and so you know but that problem of where it has to decide, not just an accident happened, but it has to decide. It made a decision to, and it had a Sophie's choice, right? The trolley problem is intentionally a difficult philosophical problem because it's a Sophie's choice, right? There's no good choice, right? Like either I'm going to kill the people in the car, the passengers and the driver, or I'm going to kill this baby that just happened to jump right, or this kid that just happened to just jump out right in front of my car. And it's kind of like, what would you do in that situation? But you know, the law is really all about corner cases. You know, it's really all about uh, thinking of good answers to hard to answer questions from a legal standpoint, right? The law in America has worked for hundreds of years because we have an adaptable and a dynamic system, and our I think form of government is so long lasting also because it's adaptable and can adapt to changing times. I mean, the world is nothing like it was in 1776, right? But we still have essentially the same government that we did 200 plus years ago. So, and I think that's partly because our law and our government has the ability to adapt to changing circumstances. And AI is certainly no exception, right? It's just another new technology that came about, except that its scope maybe is potentially a lot larger than, say, transistors or, you know, integrated circuit boards. But um, I think it's important to have some kind of balance and to weigh those ethical and moral concerns and against legal ones, rather than just, you know, blindly moving forward with all technologies, especially where technologies um, interact with people, right? So if we look at all of these industries, not all of them interact with people equally, right? So in particular, things like with health and healthcare, or maybe sports or places where people are engaged more. I think it's probably there are more legal potholes than there are in other places.
Okay, last question's a fun question. So you read a lot of books and watch a lot of movies. You already mentioned Marjorie Prime as a recommended movie. Are there any other films or books that you would recommend to the students?
Yeah, that's a great question. um, Let me see. So let me stop sharing just for 1 second, and I'll reshare here. um, let me see. So these are the books that I've read this year. um, and let's see. Well, the one you wrote, the one you recommended for the class, I thought was a good one for at least for AML, right? The You look like a thing and I love you. Um, for I mean, there's a lot of great books in general that the probably maybe one of the better ones that I've read this year was on disinformation. Maybe it's not AML related, but like
I mean, it kind of is. I
every
mean,
American should read this book.
yes.
It talks about how basically uh, the how it's so crucial for us to really be aware of disinformation and how information how we really come to form our beliefs and where we um, where people sometimes present facts that aren't really facts and the playbook of the the playbook of big tobacco that had fooled Americans for decades about the truths of how harmful smoking can be. That their playbook of essentially science denial and a counterfactual playbook and things like that are used in things like global warming and things like that. So a very, very interesting book, I would say, just about everybody should read.
Yeah, I mean, this is an area where AL is becoming, or AI/ML is becoming more and more important because that's being used to generate a lot of disinformation and misinformation.
Yes, yeah, yeah. And I think that's and one of the things I think this information overload too, and it has really caused Americans to have myself included, I'm no exception, to have I think a shorter attention span. I find myself just being pulled in 5,000 different directions all the time. And our attention is such a valuable thing, I think, nowadays. Um, and there's just a ever increasing mountain of information out there on anything, right? So it can be hard to sift through all that and to figure out what's true and what's not. Um, Let alone things that are trying to actively push false narratives as well and disinformation on top of you, which to try to figure out what's true and not is can be even harder.
Well, thank you so much for taking so much of your time to help get the students started on this course and the journey. I really appreciate it.
Yeah, thanks so much for having me, and good luck to all the students. And I look forward to future sessions with you. All right, thanks.
Thanks. Bye.
All right, take care. Bye.